You must believe me when I tell you that by the end of this video, the solution to this problem is going to jump out of your screen and squirt apple cider in your ear. Skepticism, I get it. I wouldn't believe that either, but I promise you it's going to happen. I've got another Putnam problem for you today, and it just has the most fantastic solution. We're trying to find the sum of this sequence from 1 to infinity, 6 to the n over 3 to the n plus 1 minus 2 to the n plus 1 times 3 to the n minus 2 to the n. And first things first, I'm not very good at math, so I'm just going to try plugging some numbers in, grinding through a few of the partial sums here, and seeing where we are. What do we think this series might be approaching? We'll start with, of course, n equals 1, just the first term in the sequence, which will also be the first partial sum. We get 6 to the first in our numerator, and then we're dividing it by two different differences of powers of 3 and 2. I think I said that correctly. Obviously, for our n plus 1 exponents, we're kind of incrementing forward for a second. 1 plus 1 is 2, and so we're looking at the difference between the second powers of 3 and 2. For 3 to the n minus 2 to the n, we're just looking at, in this case, the difference between 3 to the first minus 2 to the first, and as we evaluate all of that, we get 6 over 3 squared is 9 minus 2 squared is 4, so that's 9 minus 4 makes 5, times, of course, 3 minus 2, which makes 1. So for this first term, which again also is the first partial sum, we get 6/5. We're starting off at 1.2. For the second term in the sequence, which will add to the 6/5 to get the second partial sum, we're taking the second power of 6. So 6 squared over, again, we're kind of incrementing forward the difference between the third power of 3 and power of 2. So that's going to be 27 minus 8 makes 19 times, and here's where things first got interesting to me. As we plug in n equals 2, we get that 3 squared minus 2 squared difference that showed up in our first term. And so now I'm thinking, oh, I wonder if there's some kind of clever way to use that to get a common denominator for all the terms in this sequence and then add them all together and simplify nicely out to some convergent sum. Hold that thought. We'll just compute the term first of all. 6 squared, of course, is 36. We already said 3 cubed minus 2 cubed was 19, and we already know 3 squared minus 2 squared is 5. As we work this out, of course, 19 times 5 is 85, and so what we're looking at is 95. And so what we're looking at is 36 over 95, which of course we want to add to that first term, 6 over 5. Again, I'm already thinking here, oh, common denominator kind of thing. I need to multiply by that 19 over 19 and then add these together, and what I get just happens to be a little bit above 1.5. So we started off at 1.2 after just a single term, and now we're at 1.5. Now, when I jump ahead to the next term for n equals 3, I realize, oh, that common denominator thing that I thought was going to help, that doesn't actually end up being all that helpful. Keeping those terms in the denominator separated out, I can see, yeah, that 5 stuck around for 2 terms, but then it goes away. Anything that pops up in the denominator for one term does pop up again in the next term, but then cycles out and goes away. So it doesn't seem like this is actually going to be a useful way to try and combine all these different terms. It doesn't seem like a common denominator thing is going to happen here. Now, from here, I did something that obviously the people actually taking the Putnam would not have the advantage of doing. I dropped this into Desmos. I built a little toy to help me visualize what's my expectation here. Do I think that this series is going to converge? What value do I think it's going to converge to? Again, for sure, this is not like contest legal, but if you take a look, you can see pretty quickly, really within about a dozen terms, this series is converging to 2. So again, we found out it started off with 6/5 or 1.2. By the next partial sum, it was already a little bit above 1.5, and it turns out that it looks pretty clearly like it's going to converge to 2. Now, that doesn't really inform my next move here, and as a math educator, this is the part of the video that I really struggle with. How much do I show you the elegant solution that I eventually came up with versus the decent amount of time, I don't know, half an hour that I worked on figuring out that elegant solution? I don't want to go too far into the dead ends, but I do want to show you kind of a basic approach. So the first thing I tried once I decided, okay, let's dive into this expression, see if we can get a way to get a 2 to come out of it, is, okay, clearly the people who have written this up as a contest problem are doing this because there's a special connection between 6 to the n, 3 to the n, and 2 to the n. Namely, of course, 6 to the n is 3 to the n times 2 to the n. And so I thought, wouldn't it be clever to pick a couple variables and just let them stand for 2 to the n and 3 to the n, and then try to rewrite this expression in terms of those variables. Our numerator, of course, would now just be a times b, where a is 2 to the n and 3 is b to the n. No, b is 3 to the n. And then the second term in our denominator, very straightforward, it's simply going to be b minus a. But then the first term in the denominator, I'm going to have to manipulate a little bit. What on earth should the connection be between the next power of 3 or the next power of 2 and the current powers of 3 and 2? And the answer, of course, is, oh, the next power of 3 is 3 times larger. The next power of 2 is 2 times larger. In fact, of course, that's what's beautiful about exponential expressions. If we are looking at an exponential expression where we can express the exponent with addition, that can be rewritten as a multiplication. That's one of the things that makes exponentiation what it is. So 3 to the n plus 1 is really the same thing as 3 to the n times 3 to the 1, or for our purposes here, 3 times b, where b was that 3 to the n. Similarly, 2 to the n plus 1 is the same thing as 2 to the n times 2 to the first, or again, for our purposes here, 2b. Now, from here, we could go about expanding out this denominator, and it's going to give us back a quadratic, and that will actually be important later on when we get to the good solution, but it's kind of unnecessary for what my next attempt was. I thought, okay, can I do like a partial fraction decomposition here? If I can find a way to separate this expression into two different fractions, one of which is over 3b minus 2a, and one of which is over b minus a, maybe those fractions will have some kind of interesting relationship that would let us cancel out and get that the value of this series is 2. Now, the typical thing to do is declare a couple other variables, usually, honestly, a and b, so to let things not be so confusing, I'm actually going to call them c and d instead, and then to recombine this from this stage, getting some expression for the numerator in terms of a, b, c, and d that would actually let us solve for c and d and split this into two different fractions. What I should have seen but didn't when I attempted this is that's not going to be possible. Since a is being multiplied by b here, but as we look at these denominators, there are no ab terms, that ab can't come from anywhere. When we try and do the fraction decomposition thing, for example, whatever expression we didn't have in the denominator, 3b minus 2a over itself, and of course we're going to do that same thing to the first fraction using b minus a over itself. Ignoring the denominators now because they're going to be a common denominator, they're not going to matter anymore, we're going to get that ab must be equal to c times b minus c times a, coming from a distribution here, plus 3d little b minus 2d little a, again coming from our distribution here. The typical move is now to start grouping together things in terms of b and things in terms of a, which we definitely could do here, but again isn't going to help us because we have no a alone on the left side. We have no b term alone on the left side. And so basically at that stage I gave up. I worked on it a little bit more before I realized what I'm telling you now. That will not help us with the partial fraction decomposition. So then I said, you know what, let's not do this weird intermediate variable thing. Let's just actually stay in terms of 2 to the n, 3 to the n, and 6 to the n, and see what happens if we multiply out our denominator. So again, numerator for the moment, we're going to leave that as 6 to the n, but then in the denominator, I'm going to do something basically like FOIL. First terms, outside terms, inside terms, last terms. My typical preference is box method or some other kind of double distribution, but what are you going to do? Let's just call it FOIL. Now, 3 to the n plus 1 times 3 to the n would be our first term, and then multiplying the inside terms, for example, we're going to get minus 2 to the n plus 1 times 3 to the n, and multiplying those outside terms, minus 3 to the n plus 1 times 2 to the n, and finally multiplying those last terms, since they're both negative, we're going to have a positive now, 2 to the n plus 1 times 2 to the n. Now, same as we did before, these expressions that have a common base, we are going to be able to take advantage of that and simplify them a little bit using our exponent rules. Unlike before, we're not undoing the addition. Now we're going to combine the exponents through addition. So we get 3 to the 2n plus 1 since 2n plus 1 is the sum of n plus 1 and n, and over here 2 to the 2n plus 1. In the middle though, we're actually going to go back to what we initially did. If we express this 2 to the n plus 1 as 2 to the n times 2 to the first, and then of course we still have the times 3 to the n, and then we do the same thing to the 3 to the n plus 1 power, so 3 to the n times 3 to the first times 2 to the n, we can see that these end up being, in some sense, like terms. This would be 2 6 to the n's, because we can multiply the 2 to the n times 3 to the n part. Minus 2 of them, actually. And then this would be minus 3 of the same 6 to the n's. Same reason as before. 2 to the n times 3 to the n is 6 to the n. Taking it all together, that makes minus 5 times 6 to the n. And this is starting to look interesting because, of course, 6 to the n is part of my numerator. And so now I'm thinking, oh, maybe something is going to cancel out nicely here. But let's come back to that in a moment. 3 to the 2n plus 1 and 2 to the 2n plus 1, those are kind of a problem right now. I'd really prefer all my exponents to be the same if possible, just because more interesting things happen when everything is the same. That's not a good life lesson. So 3 to the 2n plus 1, one more time we're going to do this move where the plus 1 really just represents another times 3 idea, but then I have another move to do with the 3 to the 2n. The last exponent move we're going to use, I think. 3 to the 2n power is the same thing as 3 to the 2 times n power, meaning that our exponents right now have a multiplication. One way to express that multiplication is coming from a power raised to a power. In this case, I could express it as something like 3 squared to the n power. 3 squared, of course, is 9, so in fact, I can call this 3 to the 2n plus 1, the same thing as 9 to the n times a 3, again, that 3 coming from the additional plus 1 power, or writing it more like a coefficient, 3 times 9 to the n, minus 5 times 6 to the n, and then one more time over here, same idea, 2 squared is 4, and then plus 1 means 1 extra 2, so plus 2 times 4 to the n power. All right, let's bring that over. We've got an equivalent expression now for what we originally started with. Let's see if we can make it nice and centered. 6 to the n over 3 times 9 to the n minus 5 times 6 to the n plus 2 times 4 to the n. Now, is this any better? I think so. I mean, I know so. I know how the video ends. But at the time, I was like, okay, what am I supposed to do with this? My denominator is entirely in terms of something to the n, but the somethings aren't all the same, so it didn't really seem like I could use a factoring move. But in fact, that's what I have to do here. I tell my students all the time, you have to be super careful about cancellation. Just because I see that both the numerator and the denominator have that 6 to the n power, that doesn't mean that I can just kind of randomly cross them off. Basically, plus or minus signs are like glue. They're telling me that I have to be really careful about how I work with this denominator. But there is a solvent to that glue, and that solvent is factoring. We are actually going to do a little bit more factoring here, but the kind of factoring we're going to do is going to look a little bit strange. I'm going to multiply both my numerator and my denominator right now by the very same 1 over 6 to the n. Because it's the same, I'm allowed to do this, and obviously what it's going to do in my numerator right away is make a 1. That's interesting because that has no variables whatsoever in it anymore. In my denominator, one more time, I'm going to be doing a little bit of distribution. I get something like 3 times 9 over 6 all to the n power. And because they have the same exponent, I can actually combine them this way. When I distribute that 1 over 6 to the n to 5 times 6 to the n, obviously the 6 to the n part cancels out. And then when I distribute to the 2 times 4 to the n, just like we did before, I can actually combine the 4 to the n and the divided by 6 to the n part into the same expression. Now, this is a lot better for 2 reasons. First of all, like we already said, no more variables in the numerator, so that's going to make any other moves we do later on way easier. But second of all, 9 over 6 and 4 over 6 both simplify. In fact, they simplify to 3 over 2, 2 over 3 reciprocals. I know I said earlier no more intermediate variables, but let's try one more. Let's call some intermediate variable x 3 over 2 to the n power. So what that's going to do is let me rewrite this denominator as 3 times x, because of course that's 3 over 2 to the n power, minus 5 plus 2 times, now hold on a second, 2/3 to the n I can also express in terms of x. 2/3 to the n is the reciprocal of x, so I can express this as x to the negative first. Meaning essentially with this one variable substitution, I now have what's starting to look like a much simpler expression. In fact, one more move, I'm going to multiply both top top and bottom by x right now, and it's going to give me a beautiful little quadratic in terms of x. My numerator turns into x, of course, and my denominator, after I distribute this x, turns into 3x squared minus 5x plus 2. I know that was a lot of work just to get back to a place where we are going to try a partial fraction decomposition, but it's going to work this time because our numerator doesn't have multiple variables, it just has that one variable x. 3x squared minus 5x plus 2 factors as 3x minus 2 times x minus 1. My numerators I'll go ahead and call something like a plus b, and so adding these together, the first fraction I need to multiply by x minus 1 over itself to get that common denominator. I guess I'll move this equal sign a little bit. And the second fraction I need to multiply by 3x minus 2 over itself. So that gives us ax minus a plus 3bx minus 2b all over that original denominator of x minus 1 times 3x minus 2, or again 3x squared minus 5x plus 2 if we keep that expanded. Now that classic fraction decomposition move where we group together the terms that have an x and we group together the terms that do not have an x, this time it's going to work. We can say for sure that ax plus 3bx must be equal to x itself, because that's the x we had from the original numerator. And then we can also say that a minus a minus 2b must be equal to 0, because we had no numeric part in the original numerator. Ignoring the x's, of course, or factoring them out and, giving us back that this is equal to 1, we have a system of equations now. A plus 3b must be equal to 1. And then from a moment ago, minus a minus 2b is equal to 0. So now we can solve for a and b and state this as two separate fractions. Adding these together nicely gives us that b is equal to 1, and then plugging that back into, say, the first equation gives us that a plus 3 equals 1, which means a itself must be negative 2. Now recall the way we set this up was a over 3x minus 2 plus b over x minus 1, so now we can plug these values in. A is negative 2 over that 3x minus 2, and then b was positive 1 over that x minus 1. Finally, after all that, let's undo this x substitution that we chose earlier. That means we're looking at negative 2 over 3 times 3 halves to the n power minus 2 plus 1 over 3 halves to the n power minus 1. Now, I promised you cider, right? I promised you that the solution to this problem was going to pop out of your screen and pour apple cider in your ear, so get ready. I'm going to do one last clever thing with just this first fractional part. So I've got two different fractions, and as long as I multiply both my numerator and my denominator by the same thing, I can manipulate them a little bit separately. This gives us back an equivalent expression to what we started with, a sum from 1 to infinity of negative 1 over 3 halves times 3 halves to the n power minus 1, where this is coming from distributing a 1/2 in the bottom of that first fraction, also known as the denominator. Now the second fraction we'll leave alone, 1 over 3 halves to the n minus 1. But what's going on here? 3 halves times 3 halves to the n, that looks an awful lot like that exponent rule thing we were talking about earlier. Because that's a common base, I can turn that into negative 1 over the sum of those exponents, 1 and n. That is 3 halves to the n plus 1 power minus 1 plus 1 over 3 halves to the n power minus 1. Well, these look awfully similar, don't they? Except one of them has a minus sign and its power is incremented one term ahead. Do you see it? Do you feel the cider in your ears? If I plug in something like n equals 1 right now, for this negative term, I'm going to get negative 1 over 3 halves to the second, because again, n equals 1, so the next n is 2, minus 1, and then I'm going to add that to 1 over 3 halves to the first minus 1. Well, 3 halves to the first is 3 halves, minus 1 is 1/2, and of course 1 over 1/2 is 2. That's interesting, right? Because 2 is what we said was the value of the entire series. Of course, I can't ignore this first fraction. It's going to be negative 1 over 3/2 squared, so that's 9/4. Minus 1 makes 5/4, and negative 1 over 5/4 is the same thing as negative 4/5. Now, of course, if you add negative 4/5 and 2, you get back 6/5, just like we did at the beginning when we plugged in n equals 1. But the trick now is that when we increment forward, so again, this was the n equals 1 term, what about the n equals 2 term? When we plug 2 in for n, we're going to get positive 1 over 3/2 squared minus 1. That's going to evaluate out to a positive 4/5 that is going to cancel this negative 4/5 out. Now it's also going to give you back negative 1 over 3/2 cubed minus 1, which just so happens to work out to negative 8/19. But then that negative 8/19, when we go to the n equals 3 case, sorry, I'm running out of room here, it's always going to end up canceling out. Because the only difference between these two terms is that exponent, the negative term we get in some n equals 5 gets canceled out when we move to the next term and n equals 6. And then that happens again and again and again, infinitely many times. And the only term that doesn't cancel out is the original n equals 1 positive term, the 1 over 1/2 or 2, that is the value of this infinite series. Oh my gosh. As Putnam problems go, not super abstract, really rewards your ability to manipulate things algebraically. Like a reasonably talented 10th or 11th grader could probably get this done. It's mostly just algebraic manipulation. There were some false starts in there, and again, it definitely took me longer initially than me explaining it here now. But if you ask me, an absolutely beautiful summation. I love the way, gosh, the problem posers just come up with these astounding things that we would end up with basically a copy of the sequence embedded into itself that always perfectly cancels out on the next term. Very cool. Thank you to Benjamin Lays. I hope I'm saying his name correctly. Lies? That doesn't seem better. As he was the one, I originally saw him sharing this problem on Mathstodon. Unfortunately, when I followed up with him, he didn't know which test it was from, and I couldn't find it either. So if you can find what Putnam this is from, I would really appreciate that, just because I would love to know. You can throw that down in the comments below. What did I do wrong? What did I not go through quickly enough or elegantly enough? What's the shortcut that I missed? You can let me know that as well. And otherwise, I will see y'all next time.